So up till now, we have been studying about different circuits, different techniques where the clock was not involved. Now we have to look for a circuit design technique where we want to synchronize our input and output signals. So that technique is known as clocked CMOS logic circuits. We have earlier examined about the static CMOS circuits. But now we will discuss about the clocked CMOS circuits. What is the clocked CMOS circuit is? It depends on the clock signals. It is normally known as C2MOS circuits. So the clock signal like phi, which is represented by a phi, is periodic. Obviously we are talking about a clock. So this has a periodic signal. And this period the frequency of the signal can be represented by f is equal to 1 over t, because the t represents the time period of our clock signal. And correspondingly, we can say that there could be two different clocks. One is our phi clock, the other one is our phi bar. And in ideal case, these clocks are non-overlapping. Like if this is 1, this should be 0. This should be 0 here. If this is 1 and this should be 0 here. So we can say that this condition must be satisfied because phi dot phi bar is equal to 0. If you apply a NAND gate on these two clocks here, you will get a straight 0 line, a flattened 0 line. So how this clocked CMOS circuit look like? Like we have our NFET logic here. This NFET logic was designed earlier when we were talking about how we can design our circuits, or how can we design our CMOS circuits using our equations. So these two are same, like we have been studying it many times earlier. And what is the difference is we have two MOSFETs here, and we are talking about an input clock source here. We are not talking about enable signal here. Now this will be controlled by a clock signal. So what happens is when our phi is equal to 1, phi is equal to 1 here, and phi bar is equal to 0 here, it means this circuit is conducting, like PMOS is conducting and NMOS is conducting. So it means that the Vout will appear across this Cout circuit. Depending on our input, either it is NFET is conducting or PFET is conducting. For example, if our PFET is conducting, this Cout will be charged. And if, for example, if this Cout is charged at time 0, and there is a clock signal which basically turns on this NFET and this PFET, so this charge will be held, this charge will be stored. So it means that this charge will be held for some time, and the previous output can be kept, obviously, which we have observed here. So the new output can be appeared at this output terminal only in case when we have our phi is equal to 1 signal. Because when phi will be 1, this will be active and this PMOS will be active. So the new logic can transfer their output at this Cout, this capacitor. So if we want to see in this diagram here, we can say that the clock signal, the phi clock signal, has only two points where we have valid inputs. And these 2 points also represent that we can write, read, or whatever operation we want to perform. We have to basically detect this high state. Then we have valid inputs, valid outputs, and we can read that output from this terminal. In other case, this will represent a high Z state, like we have seen in the tri-state circuits. So this can be represented by a high Z state. And obviously we can see that here, if these two are cut off, this output terminal is in a high Z state. So I have made one comment here, the voltage across Cout is held for some time. why I have said it? Because there will be some leakage current present which will eventually discharge this circuit. So let us now solve some expressions to basically understand the phenomena of like this hold time for this C out capacitor here. So we have been talking about the clocked CMOS circuits, or it is also named as C2 MOS. So what we have to understand is what is the what are the bases for charge leakage. So to understand the basis for charge leakage, let us draw a simple circuit here. Like for our inverter circuit, we are considering, like, we are obviously not talking about the pull up and pull down networks. We are just connecting the middle part of our clock CMOS circuits, where we have input as like this is phi bar is equal to 1, and this phi, like at this point we have phi is equal to 0. It means both these transistors are in cutoff region. And like we are not talking about what is connected on this side or what is connected on this side, because both these transistors are in cutoff region, so we are not talking about other terminals. Even our transistors are in cutoff, still there is no possibility that all current will be blocked, because there is some leakage current that flows in or out, obviously out of the device. There could be different possibilities, like our current may flow, like leakage current may flow in two directions. Either it will flow into the device, or it will obviously flow out of the device. There could be possibilities like this current may flow in two directions. So to understand this, we have to consider two different cases. In case 1, like we are talking about this, we are talking about this PMOS here. Like in our case 1, we assume that this body of PMOS was connected to VDD, and what this body is, in our case 1, the body of our PMOS is connected to VDD, and this is normally known as bulk. And what this bulk is, this is basically our N-well region. And if this N-well region is connected to our VDD, like this N-well is connected to our VDD, this means that there will be a PN junction appearing on like P plus and our N-well. So we can say that for our PFET, we have like P plus region, and then we have our like N-well region. There will be a PN junction, and this PN junction may be represented somewhat like this diagram here. Consider we have N-well here, we have our P plus region here, and obviously this is if this is our N-well, we have this PN junction here. The current will flow like this is connected to VDD as well. So the current will flow in this direction here. The current will flow here. So this current is represented by I of P, like the current that flows from in the PMOS. So this is a small current that flows onto the node, or we can say that this current flows into the device. So we can say a small current flows, like this current is IP, flows onto the device. onto the device. Or we can also say same phenomena can be applied on our NFET. Like this NFET's body is connected to ground. This NFET's body is connected to ground. It means that we have another PN junction here, and if we have a PN junction here, the current will be flowing out of the P substrate, or we can say that the current will be flowing out to the P substrate. So we have a different case, like we have a case 2 here. For our NFET, current will flow out of the device, and this current is known as I of N. If we represent it here, like if we represent it with different color, like this is represented by I of T and this is represented by I of N, and we have a capacitor that is attached to this point. Obviously this capacitor is RC out, and there is one current that flows and it is named as I out. That current may be flowing out of the capacitor or into the capacitor depending on our circuit connections. And obviously there is a voltage that is applied that basically appears at this terminal, plus and minus terminal, and this voltage is represented by V out of T, or simply you can write it as V of T. Let me make it a bit simpler, like this is our V of T. This voltage appears at our output capacitor, and we are mentioning it as a function of our time. We are saying it as a function of time because we have said it earlier, the output voltage cannot hold for a longer period of time. So if we consider, and the output capacitor has some initial value and initial charge, so we consider a case when capacitor has some initial value. So then we can say that the current that flows out of capacitor is I out. And if we apply KCL on our output terminal, then we will get V out is equal to I of N minus I of P. So this is our output current. And if we want to know the equation for the output current that basically leaves the capacitor, that can be found out to be dV by dt C out and dV by dt. So this expression shows that the current flows out of the this negative sign shows that the current basically current leaves the capacitor. So current here does leave the capacitor. So if we want to see the effect of leakage currents, we have to assume a case when at time 0 we have capacitor charged at some voltage. So to see the effects of leakage current, we have to assume at t is equal to 0, capacitor is charged at a voltage, or we can say that at t is equal to 0, capacitor is charged to a voltage that is known as V1. And we can also say that V of t is equal to V1, or we can write it as V of naught is equal to V1. And in case when our current that flows to the ground or to the NMOS is greater than the current of our PMOS, like for example, if IN is greater than I of t, then we will have, like we can say that the I out will be positive. Why we say that is because we have this expression I of n minus I of p. Like if this is greater than this value, obviously this whole expression will be of positive quantity. So let us represent this quantity as a voltage, that is our leakage voltage. We can say that this is a positive quantity that we have been represented it here. So we can write the expression as IL is equal to minus C out dV by dt. Now we have to solve this expression for this dV here. dV is equal to minus IL divided by C out and dt. And obviously here these two quantities, like these two quantities here, are constant. So the variations we have is like here the voltage varies and obviously the time varies. And the variations are like, let us consider the voltages, the limit of our voltages from like V1, because we have considered initial value at our capacitor is V1. So V1 to V of t, and obviously the time varies from 0 to t. So if we integrate this expression here, if we integrate this expression, this one here, we will get an equation like this is V1 and V of t dV, this is equal to minus IL divided by C out integral of 0 to t and dVt. So the expression would be equal to, like let me write it something like the expression here, the integral here. So this expression would turn out to be like V of t minus V1 is equal to V1 minus IL, sorry, this is not V1 here, this is minus IL divided by C out and t. And if we solve expression for V of t, then we will get it like V1 minus IL divided by C out and t. So this expression is for our voltage, like voltage with respect to time. If we plot this expression here, the V of t, this V of t would be something like this value. Like here we have our voltage on our y-axis, on our x-axis we have our time. So initially we had a value, like we had this value that is represented by V1, and we say that this voltage decreases and it reaches a minimum value. Or we can say that if we plot this graph, it will be something like this. And if this graph decreases, we have to find a level when this crosses our minimum logic 1 level. If this is our logic 1, it means that there is some range over which our voltage can be represented as logic 1. So this is our point where we can say that this is our minimum of logic 1. Below this point here, we can say that this is our logic 0. So we have to find the time which is required to drop our initial value to our minimum value. So this point is represented by, like this point here, it is represented by V of x. So here this point is represented by V of x, and this time here is represented by T of h. T of h means the whole time. So this time, the whole time is basically the maximum time that the logic 1 voltage can be stored. So we can say that max time for which logic 1 can be stored. So this is the maximum time for which we can hold the logic 1 state. So it means that the voltage will drop depending on our time and because of the leakage current. So we can write this expression, this V of t expression here for this whole time here. V of th will be equal to V1 minus IL divided by C out th the whole time, which is equal to Vx. If we solve this expression for the whole time, this turns out to be th is equal to C out divided by IL V1 minus V of x. So this is our expression for the whole time. To understand what this whole time means, let us solve an example, or we can solve the value of th for a simple case where we have C out is equal to, like this example here, this C out is equal to 50 femtofarad. We assume that our leakage current is around 0.1 picoampere and the voltage change from V1 to Vx is equal to 1 volts. Like we are talking about this value here, that is around 1 volts. So if we solve this expression for th, and if we put these values here in this expression, we will get a th of 0.5 seconds. And if we observe, this th is basically like very small quantity in our real world, where we deal in seconds or minutes or in hours. But if we talk about the semiconductor devices, we can write it as like this is represented by 500 milliseconds. If you observe this time, this is a huge number. Like this is a huge time that basically represents a whole time. So we can say that the fast clocking can help solve the issue of our leakage current. If we have a faster clock, then there will not be an issue of our leakage current, because it will switch faster. It will discharge our capacitor before it discharges because of our leakage current. So we can conclude that it is not possible to idle our clock signal in our CMOS circuits, because if we make our clock idle for a longer period of time, it will discharge our capacitor at our output and we will lose our the output value. So the conclusion can be written as, like it is obviously it is not possible to idle the clock signal in CMOS logic circuits. And we have seen that why we cannot do that, because it will eventually like discharge our full circuit. So the other case is, like we have considered a case when our capacitor was charged, but the other case could be like when our capacitor was not charged, the output voltage was 0 volts. What will happen in the other case? Like we can say that second case, when like V of 0 is equal to 0 volts. And if our V of 0 is equal to 0 volts, we can assume that our full current, the IC current, is equal to IP minus I of n, because we are considering like this is a positive value. And why we are considering it is a positive value? Because we want this capacitor to be charged. So that if this is a positive value, then our capacitor will be charged. And V of t can be written as IC divided by C out and T. So this IC here, this IC basically increases this voltage in time, and it means that the logic 0 may drift. And like the other thing, what we can say from this statement is a minimum frequency requirement. So we can say that for the case 1, like in this case, we had represented a higher frequency requirement, a maximum frequency requirement, where we have to operate. And in this second case, like in case 2, when we are charging our output capacitor, we are talking about a minimum frequency requirement. So the maximum frequency requirement basically tells us how much time we need to store our output charge, and the minimum frequency requirement tells us about how long can we hold our 0 logic level. So this is a limitation for our circuits. So in addition to our leakage currents, there are different types of currents which can affect our the whole time behavior. For example, in addition to our leakage current, we have like issues of physical structure, and we also have some issues of materials which are used. So these two factors also add up to the leakage current. Like this may take our leakage current to approximately 10 power minus 7 ampere. If we solve the same expression for whole time that we have done earlier, this whole time turns out to be 0.5 microsecond. It means that it was earlier 500 millisecond, now it is reduced to 0.5 microsecond. So it means we have less hold time for our output capacitance, output charge at our output capacitance. So if our leakage current increases, like if we increase our leakage current here, like if we increase our IL, this means that our hold time decreases, and if our hold time decreases, we need faster clock so that we can operate our circuit correctly. So to conclude all this discussion here, we can say a couple of we can summarize it in a couple of statements. One is like the charge storage on a capacitor node is a time limited event. And secondly, we can say that this places important constraints on our logic circuits. So concluding this session, we can say that if we're designing our clocked CMOS circuits, we have some limitations for our frequency, because the output capacitor cannot hold or charge for a longer period of time, and similarly it cannot be in a state 0 for a longer period of time. So this basically adds our conditions for high clock signal, high frequency clock signal and low frequency clock signal. So this was for our clocked CMOS designs. I will leave you with a simple question here, which you may try it yourself. Like, the question is, like, how can you design clocked CMOS logic for NAND and NOR gates, and also the layout of circuits. So we have talked about only the inverter case. Now you have to basically design the NAND and NOR gates, and also obviously the layout of that circuits. You can compare the layout designs and these CMOS circuits with the other design processes that you were performing in your previous design practices. So this is it for this session. I will see you in next session, inshallah.